Everybody, this is Larry. This is day 28 of the February Leetcode Daily Challenge. Hit the like button, hit the subscribe button, join me on Discord or Twitch or whatever you like. And let's go over today's problem, maximum frequency stack. And usually I solve these live, so if it's a little bit slow, fast forward or skip ahead, whatever you like. But okay, let's take a look at today's problem. Maximum frequency stack. Implement frequency stack, okay. A class which simulates a stack operation, push, pop. Okay, what does this mean? Okay, you have a push and you have a pop. Pop removes the most frequent element in the stack. If there's a tie for topmost, the closest to the top. Okay, so I think this, I remember working on this one. I mean, I definitely solved it, but I don't remember the details. So that's my little caveat. So like but I'm trying to remember what I did. So maybe, or just try to figure it out, and probably should just figure out from scratch a little bit. Okay, so the push, we just keep pushing, and then what the element closest to the top is removed, and then return, and then it becomes, okay, let's see. I have some questions about this problem, that's what I'm trying to take. So you do this, okay, we push all these things, you pop the 5. Oh, you pop, which 5 do you pop? Huh? Oh no, this is the initial array, that's why. You pop the 5, and then now you have you pop the 7, and then you pop the 5 again, and then you, okay. I think this is a little bit of a weird problem because so I definitely have a n log n solution. I'm trying to think whether I need a linear one. Or just that I can figure out that there is a linear solution in general. So the n log n solution, the n log n solution is just we push everything on this. I'm going to try to solve it as fast as not as fast as I can, but in the n log n way, and then we could maybe go through the discussion or something to see if there's a linear time one. And then I definitely remember solving this one as well, so we could see how past Larry solved it. We'll do all those things and see how much I learned, right? Because I don't remember it enough to know. So basically, the thing that I'm going to do is, and you can actually keep this. So you can actually keep this in the way to solve this in n log n is by keeping things in a tree-like structure that allow you to keep things sorted, and then removing the biggest element from that, right? And in theory, there's a way to do this with a heap, but it's a tricky way to do it with a heap, so I'm not going to do it with a heap, because it's similar to, there's a way to do it with a heap such that it is similar to the Dijkstra's algorithm, where you have a heap and then maybe we could do it that way, but I'm going to do it another way. Like I think you could do it with a heap, and if you're trying to solve it with using a heap, my hint to you with respect to that is you solve it the same way that you do Dijkstra's algorithm, where there's a perfect heap where you're able to remove stuff inside the heap, and then there's the amortized the same complexity but slightly slower heap where you do an amortization step where you just remove stuff more than once, but so it's technically slower, but it's still n log n. But the key for solving this problem is just keeping a data structure so that you have three items on a key. You have, what are the 3 items, right? You have the value itself, you have the frequency, and then you have the index, which is the top. You know, when maybe the index, but actually maybe time, right? Which is the times when was it last inserted? Is that good enough? No. Yeah, because once you yeah, okay. Actually, do I want to do it that way? I was going to use sorted list, but now I think about it, maybe it's not the way that I want to do it. So I think what I'm going to do is actually, I'm going to do it another way. Okay. I know that I've been jumping back and forth, and I apologize for that. But what I'm going to do is, so this is a data structure problem. So I think it's kind of hard for me to explain the thought process a little bit, because my thought process in this is just like, because there's no, the problem solving, part of a data structure problem is kind of figuring out, like almost like Lego pieces. You have all these different data structure and trying to figure out how to interact with, like how to get the interaction in a way such that the complexity is fast enough. And for this, I am going to actually end up using a heap, and yeah, I'm going to use a heap and a dictionary, right? And what am I going to do? I'm going to explain this while I code, because it is a data structure problem. So what I'm going to do is I'm going to have a dictionary that maps. Basically, what I want to do is keep a stack for each number, that keeps track of when we, like the timing of when each number gets pushed to that mini stack. So basically, let's just say stack by number is equal to collections dot default dict of let's just say a list, because we use a list to do stack, but and then we have a self dot time, as we said, so we start that at 0, and then let's have a heap to keep track of all the things that we have on the heap. And okay, so now that we have that, we can figure out what it means to be a push. So the push, well, first of all, let's add the time by 1, and then now our stack by number, we take this number and then we append the time by it. And you could actually do a increment before or after, it doesn't matter, because as long as you're consistent about it, it doesn't matter. And then here we now I was thinking of something, but then I forgot that if you do remove it. Wait, no, I think I'm just confusing myself. I think this is right. So then by pushing, oh no, you have to remove the thing that's inside already right now before you push. That's why. Man, I think I got a little confused here. Okay, fine. I am going to use a sorted list for this, because it makes it easier for me to kind of reason about it. So let's say we have a sorted list, and it's an API that basically keeps a list that is sorted. It is what it sounded like. And then now to insert it, and the way that we're going to use it is kind of just to get the max value of something. And the key that we're going to sort by, in this case, it's going to be two things, right? One is the frequency, as we, that makes sense. And then we're going to sort by the last time inserted, which we will keep track of. And then we also just keep track of the number, right? So X. So then now we want to insert it into the list. But before we push it, we want to remove what's inside, right? So here, so we have to keep this invariant of if this thing, if the length of this is equal to 0, what does that mean, right? That means that we can just, that means that we don't have to remove it. So that means that if this is greater than 0, we have to remove the existing entry, right? And the existing entry, it's going to be self.sorted list that, I think it's called that remove. The existing entry is just the frequency, which is the length of the self stack by number of X more specifically, So this is the frequency, right? You could also use it in another lookup table, but the length of this is the frequency, and then the time is the previous time. So this is going to be the top of the stack because we keep track of this thing. So this is top of the stack, and then the value, which is x. So we remove this so that we can update it by appending this to the stack, and then now we can add this new thing, which is actually pretty much the same. Now we can add this thing, which is just that we updated it. So basically what we want to do, and why this looks funky, is that in this sorted list, we want to update this value with its new value, because now we push the new thing, right? So the same thing goes for pop. So the pop is, now we looked at the sorted list, the biggest element, which is the item that has the most frequency, with the tiebreaker being time, and then x is the value, right? So then or the return value is equal to the last item, the x value, which is the third key. So this is what we eventually return, and then now we have to update the sorted list. So then the previous value is going to be let's see, yeah, so the previous value is good. Yeah, the same thing similar to what we had before, which is we have the length of the self.stack by number of our value, and then self.stack by number of the well, actually, I don't know why I did it this way. You could just remove the last number, right? Or yeah, the last item. So that's just this, right? Yeah, okay, let's actually write it out. Last item is equal to the biggest item, right? Or the, yeah, and the right value is equal to the last item of this, and then now we could remove the last item, and then now we have to put in the updated item back into the sorted list. I know that this is really weird code, but so which is oh, the new pop. So we have to do one more thing, which is that we have to pop the stack by item, by number rather, of, let's just call this x so I could copy and paste. We now want to remove the last item, right? And then now we do the same thing with here, which is now we update, we do the update, and then that should be it. And again, so these operations, depending on your language, can be done in a tree-like structure. So, so you just have to be able to, and there's a lot of what I call bookkeeping. And by bookkeeping, I mean just keeping track of where everything is, and then removing it, updating it, and then put it back in a sorted way. Oh, is that really? Oh, from sorted containers, import sorted this. Let's give it a go. Let's give it a spin. And ooh, no. Oh, typo. Let's now give it a go. Give it a spin. And hopefully that's one-time error. Oh no. Line 24. Oh, I have to check one thing, which is that obviously this, we should only do this if there's still an you know, if there's still a number left. Otherwise this doesn't make sense. Okay, so this looks good. Let's give it a submit. Sweet. So let's go over the complexity real quick. Let's see. So let's say, you know, let's say we have O of P plus Q. Oh, sorry. Let's define something. Let's say we have P is equal to pushes, Q is equal to pops, right? And N is equal to P plus Q, because that's the max number of number, right? Then in this case, so each push, you know, sorted list removal or tree removal, if you want to think of it that way, will be log n. This is just a stack operation. This is O1, so this is also log n. So in total, this is going to be O of log n. Pop is similar, right? We look at the last item, which is log n operation or whatever, depending on how you want to define it. But either way, this is also going to be log n. And well, if this is the last item, I guess it doesn't have to be log n. But in any way, for a tree operation, this is going to be log n because you have to add it back in and maybe anywhere, right? So this is, oh, I will, I don't know why I will log n, even though I said log n a few times, right? So that means that for each push operation, it's going to be p log n plus q log n, or obviously, oops, over p plus q log n, with the parentheses here. So yeah, that's basically the time complexity. And then the space complexity, of course, is just, we have a sorted list, which is linear. This is awkward looking, but it's linear because each item that we come in will occupy one space on the stack by number. So it's just transformation of the input. So it's gonna be linear space. So yeah, that's all I have for this problem. So I'm gonna do two things. One is I'm curious if there's a, I don't know, but I'm curious if there's a linear time solution. And then two is, let's see how Past Larry did it, right? Let's check it out. Loading. Oh, one solution. Well, okay. Bucket sort doesn't really. What is this O1? All right, let's take a look. Did I misunderstand this problem? How is this O of 1 solution? Oh, I see. The push and the pop is O of 1, not that the entire thing is O of 1. We analyzed it in a little different way. I mean, this is definitely the way to do it. So we have two stacks is how they did it, right? Wait, what? Not sure I understand. All right, let's see how Past Larry does it. This is not. How is this with detailed explanation? This is just an explanation. What? This is such a lie. There's no detailed explanation at all. Okay, anyway. I feel like I've done this, but maybe not if it was in 2018. I thought I'd done this though. But let's see how Past Larry did it. Let's check that out. Let's see. Oh, this was a hard. Oh, it's either that or it was in binarysearch.com, maybe. I don't know. Let's see. Okay, no, I did do it at some point, but oh, I did it last time with a heap. It seems like. So I did the same thing last time, but with a heap. Okay, actually this way of doing it with the heap also makes sense, but actually this is way better than the way I did it today. I wonder if this, I might already have a video on this, so I don't know. But I sometimes you solve things different ways in different days. This is way better, and if I have a video on it, I'll send you a link and you should check that out instead. Whoopsie. But thanks for swinging by. That's all I have for this problem. I'll see y'all later. Take care of yourself and take care of others if you can. Stay safe, stay healthy, and to good mental health. I'll see y'all later.